In the first part of this question, we're asked to make the equation of the median b to d. So median is one of the definitions we need to know in straight lines. So median, altitude, perpendicular bisector, they're really the key often to unlocking these questions. So in part A, we're trying to make the equation of this line here. Anytime you're making the equation of a straight line, you're going to be using the formula y minus b equals mx minus a. And to use that formula, we need two things. We need the gradient of our line, and we need any point on the line AB. Doesn't matter which point you've got, any point on the line will do. We've already got point B, that's given in the question, so we've already met the criteria of having a point. We just need to find our gradient. To find the gradient, we're going to use the gradient formula. We'll need a second point on the line to use that formula. So we're going to use the gradient formula on points B, which we've already got, and point D. D we don't have, but we know it's the median, so therefore, by definition, it's a midpoint, because median means midpoint. It's the midpoint of A to C. So let's start by establishing the coordinates of point D. Point D, this lies between A and C. So you can just look, for example, at the x-coordinates and realize that between -5 and -3 is -4, or you can use the midpoint formula, adding those together to make -8 and then divide them by 2. Maybe for the y-coordinate that's easier, so add these together. -12 plus 6 would be -6. Divide that by 2 and you'll get -3. So either using the midpoint formula to get midpoints or just doing it intuitively. So that gives us point D. So that means that we can now make our gradient. So we can make the gradient using the m equals y2 minus y1 over x2 minus x1 formula. And we're going to be using these 2 points because they're the points on our line. So I'm going to make that -8 minus -3. You've got to be careful with the negatives in this question, but already you should have an expectation that because this line is sloping down to the right, it should have a negative gradient and quite a shallow line, a shallow gradient. So it should be a fraction really, something less than 1. And then we're going to divide that by 11 minus -4, so again being careful with the double negatives there. So just tidying this up, let's see what we get. So on the top we're going to get -8 plus 3, which is -5, and on the denominator we're going to get 11 minus -4, which is 11 plus 4, which is 15. Simplifying that by dividing top and bottom by 5, and we get -1 over 3. So two things there. First of all, it's come out to be negative, which is what we expected because of the direction of the line, and it's come out to be a fraction, showing that it should be a shallow line, which it clearly is. So that looks good. So we've got our second criteria, the gradient, and we can plug that now into our equation. So you can choose either point on the line. I'm going to maybe go with this point on my line. It doesn't really matter, you'll get the same answer either way. So we're going to be going y minus the b, which is -3 in my case, so y minus -3 equals m, which is -1/3, x minus the a value, which in my case is -4. So it's quite a nicky question, this one. There's quite a lot of double negatives, so that becomes a double negative to give us +3 equals -1/3 x plus 4. You could multiply out the bracket at this point. I'm going to choose instead to get rid of the fraction by multiplying everything by 3. So this becomes 3y plus 9 equals -1 times x is -x, -1 times 4 is -4 like this. So we're going to get 3y equals -x, -4 minus 9 is -13. And then just putting that back into the correct format, the y equals mx plus c format for a straight line. So we get y equals -1/3, just dividing the -1x by 3, -1/3 x minus 13 over 3. So it's a slightly ugly looking answer, but that is just the way this one's come out. Checking this number, -13 over 3, that's approximately -4. That is a y-intercept, remember, so that number could be -4 based on the other point. So that just gives you a slight orientation as to whether the answer could be correct. Okay, so quite a lot of work in that one. Let's move on to part B. Part B is a similar question. We're trying to find the equation of a line. This time we're trying to find the equation of the altitude from A to E. So altitude's a different definition. It means it meets the other side at a right angle. As soon as you see right angle, you should be thinking, well, what are the rules to do with straight lines and right angles? But again, ultimately, it comes down to finding the criteria to use the y minus b equals mx minus a formula. So what do we have? And what do we need? Well, we need the gradient and we need a point on the line. So do we have any of those? Well, sure, we've got a point on the line. So again, that criteria has already been met. That criteria is quite often met in these questions, and it's more to do with finding the gradient. The gradient we can find by using the altitude definition. So altitude means that these lines are perpendicular. They don't look especially perpendicular on my diagram, but they are by definition perpendicular. That means that we can find the gradient of B to C and then use the rule for perpendicular gradients to find the gradient of our line A to E. So let's start by doing that. So let's find the gradient of B to C. So using the subscript B to C to identify the gradient of that line. So using points B and C and just using our normal gradient formula, the y2 minus y1, etc. So I'm going to go 6 minus minus 8, again watching out for double negatives and things like that, divided by minus 3 minus 11. Okay, so 6 plus 8 is 14, minus 3 minus 11 is minus 14, so that would come out to be negative 1. And if you think about that line there, that's the line we've just found the gradient of, that is sloping down the way to the right. A gradient of 1 is 45 degrees, so that negative 1 is 45 degrees going that way. That looks absolutely perfect, so we're happy with that. Because that line is perpendicular to the line AE, perpendicular gradients should multiply together to make minus 1. That is a rule. If you multiply two lines' gradients together and they're perpendicular, they should come to be minus 1. So the other gradient, the perpendicular, has to be 1 because that times that should be minus 1. So that gives us the gradient of A to E. So that now means that we've met both of the criteria, so we can plug the numbers into our equation. So y minus, we've only got one point to use this time. We don't have point E, we've only got point A. So y minus minus 12 equals the gradient, which is 1. You don't need to write in the 1. I'm just going to write it in just to show like what's going on there, but generally you wouldn't write that in. The A value is minus 5, so it's going to be x minus 5, like this. So that becomes y plus 12. The 1 we can ignore, therefore the outer bracket we can ignore. X minus minus 5 is x plus 5. Then just moving the 12 over to get y equals x. 5 minus 12 is negative 7. So let's just check that. Could that point be at negative 7? My diagram's not great actually. There should have been a bit of separation between those points. I think this line maybe should have been a little higher up. Anyway, let's not worry about that. Yeah, it could be negative 7, so it's in the right ballpark. Okay, so that gives us the equation of the altitude A to E. And then the third part of the question is to find the point of intersection between the two lines. So yeah, to find the point of intersection, we're just basically going to equate our two equations. So that's a technique you can use for any types of function. If you just equate them, you will find where they intersect. These are straight lines. You can do the same thing with parabolas or any other type of function. So just setting these equal to each other. So we're going to get this one, which is minus 1/3 x minus 13 over 3 equals x at minus 7, like this. And then we need to solve that equation, which is not easy. It is quite a tricky equation to solve. I'm just not very happy with my diagram here. There should have been some separation between these points. So if we make that the line A to E like this, then this point B to D should have been a little higher up. So let's pretend that that one went more like that. Because the way it was in my diagram, it looks like these points intersect on the y-axis, which they don't. They intersect like over here somewhere. Okay, so now that my diagram is slightly fixed, let's go ahead and try and solve this. So we've equated our two functions, straight lines in this case. We need to solve this. Let's multiply everything by 3 to get rid of the fraction. So if you multiply this by 3, you would just get minus x. If you multiply this by 3, you would get 13, and then we get 3x minus 21 on the other side. So we need to gather our x's and our numbers together. So I'm going to take the negative x to the other side. So I'm going to get 3x plus x, and I'm going to take the 21 minus 21 to this side to give me plus 21. So 21 minus 13 is 8, so we get an 8 on this side, we get a 4x over here, solving that to give us x equals 2. And this is why I wanted to fix my diagram, because we're trying to find this point here. So this point, could it be at 2 along the way? Well, yeah, sure. It looks to be in the right place. So we're happy with that 2. To find the y coordinate that goes with this, we can just sub into either of our lines because the point lies on both. This one's horrible. This one's the smarter choice, obviously. So we're going to get y equals our x value, which is 2, minus 7, which is minus 5. That tells us the point of intersection is at 2, minus 5. So just checking that on the diagram, on my newly modified diagram. So could this point be 2 along, 5 down? Well, yeah, sure, it's in the right ballpark. So quite a long question, that one. Quite a lot of stuff going on there, using a lot of the straight line rules. In this question, we've been asked to find the integral of this function with respect to x, which really just means evaluate the integral, so take the integral basically. So all integration and differentiation questions, you need to check, are the terms in integratable or differentiable form? So these two are fine. This one, the square root, that's not integratable. So we need to start by changing that using one of our indices rules. I'm going to drop this bracket as well. The bracket doesn't really need to be there. So this becomes 6x to the 1/2 power. So remember, a square root and a half power are the same thing. The other two terms are fine. So remember, we're not integrating at this point. We're just getting all the terms in an integratable form. They're now all good to go to use the power rule. Power rule says just increase your power by 1. So the 1/2 power goes up to a 3/2, which is 1/2, and then divide by your new power. So dividing by 3/2. Next term, be careful because the minus 3 power, you're adding 1 to that power, so that goes up to a minus 2. It's very tempting to make that a minus 4, but that would be taking 1 off the power. We're adding 1 to the power. Once you've got your new power, we're just dividing by that, so over minus 2. Constants like a 5, integrate, remember, to 5x. And because this is an indefinite integral, we need to put our plus c, constant of integration, on the end. Now we're just basically tidying up. So this can look a little tricky. So effectively what we're doing there is 6 divided by 3/2. When you're dividing by a fraction, you can flip it and multiply instead. So dividing by 3/2 is the same as multiplying by 2/3. 6 times 2 is 12, divided by 3 is 4. So that evaluates to 4, the number part. So this becomes 4x to the power of 3/2. The minus 4 divided by minus 2, well, that becomes a plus 2x to the power of minus 2. The 5x stays on the end, as does the c. Now we're just checking to make sure, is everything in a fully simplified form? There's nothing really much we can do with the first term, so leaving that 4x to the 3/2. The negative power on the second term can be fixed if you like, so this becomes 2 over x to the positive 2, or 2 over x squared. So taking this to the bottom of a fraction, which is a common indices rule, to turn the negative power back into a positive, and then just leaving the 5x and the c on the end. So that is the end of that question. In the first part of this question, we're asked to make the vector b to e, but we're asked to write it in terms of p and r. So this is quite a common vector pathway question. So if you look on the diagram, which I'm looking at over here, b to e can be written as, well, remember, b to e is just how do I get from point B to point E. So if we start at point B, we can go to point A, and then from point A to point E. So in other words, you can break the journey down for part A of the question, so that you're making this journey, which is what vectors are all about, from B to E, by going from B to point A, the first part of your journey, and then adding to that A to E. So if you're ever making vector pathways like this, the joining points, if you like, have got to be the same, because you can't just, leap from one point to the other. So we're starting here, going to here, and then we're resuming the journey there and going to there. So that's basically how we go about this question, and then we just need to plug in the P and the R equivalents for these. So we don't have B to A in the question, but we do have A to B. So B to A and A to B are just the negative of each other. So this is a negative, B to A is a negative of A to B, and then A to E, we do have in the question, which is little r. I'm just going to leave that as uppercase letters for the time being. So A to B we know is P, so this is going to be minus P, and then we're adding to that A to E, which in terms of P and R is just little r. So really all that is saying is you start at point B, you go along to point A, which is the vector negative P, and then from point A you go up to point E, which is the vector r, just like that. So pretty typical vector pathway. Part B is kind of similar, but maybe slightly more complicated. So we're trying to do a similar thing. We're trying to get our way from point E to point F, so making the vector E to F. So just checking my diagram again. So if we're at point E, trying to get to point F, we can go, there's various ways you can go, and you always get the same answer regardless, but some ways are going to be more efficient. So let's go A to E, and then A to B, and then B to F. I think that's probably going to be the best way, is it? Or maybe not. No, actually, let's go from E to B, and then just straight from B to F. Yeah, that would be simpler. So we can go from E to B, and then we're going to add to that B to F. So you can always check whether you've got these in the right order, because if you add a whole bunch of vectors together, it doesn't matter how many, the start point and the end point should be the overall journey. So start in here, end in here, which is what we're trying to achieve. We're just using point B as like an intermediate sort of point. So again, we don't have E to B in the question, but we do have from the part A, the other way around, B to E. So we can just say that E to B is just a negative of B to E. And getting B to F is a little bit tougher. So we need to use information in the question. So we're told there that point B to C is split by point F in a ratio of 3 to 1. So that tells us that if you go 3/4 of the way along from B to C, that is B to F. So B to F is just 3/4 of the length of the line, if you like, of B to C, the vector B to C. So that part's a little trickier, but just by using sort of the ratio there, that's what it's going to be like. And then we can just start to plug in our numbers. So, or plug in our P, Q, and R, so our small lowercase vectors. So B to E, we already made in this part of the question. So we're going to be taking the negative of all of that. Because it's a negative of more than one term, we're going to use a bracket. So we get minus P, and this just works like normal algebra. These are vectors, remember, but it works like normal algebra in the sense of using brackets and things. And then we've got 3/4 BC. So BC is going to be, by the diagram, the same as A to D. So if you look at vector BC and you look at vector AD, they're the same vector. If you've got a vector like here and the same, and a line's parallel over here, they are the same vector. They don't need to be in the same position in space to be the same vector. So vector BC and vector AD are the same, but we know the vector AD is just little vector, lowercase vector Q. So that is just basically Q. And then all we need to do is to sort of multiply out the bracket. So minus minus P gives us P. And remember, you're distributing that minus to the R as well. So it's going to be minus R, and then just plus 3/4Q. So they tend to be a little bit challenging vector pathway questions, but yeah, a little bit of logic and a little bit of vector rules required for that one. So in this question, we've been given a recurrence relation, and we're told that we can use it to model the population of the mice in the forest, and we're asked to find, or to state actually, the A and the B value. So notice that if it's a state question, there shouldn't really be a lot of work in, sometimes no work in to actually do. So we've got to interpret the information here to make the recurrence relation, which will basically give us the A and the B value. So we're told in this question that the mouse population is going to decrease, so it's going to decrease by 2.7%. Well, if you decrease something by 2.7%, what you're going to be left with is 97.3%, okay? Just obviously, right? Because if you start at 100%, you take away 2.7%, you're left with 97.3. But as a decimal, 97.3 is the decimal 0.973, and that's the numbers that we work with in recurrence relations, not the percentage value as a percentage. So that tells us our A value, and you just need to know something about recurrence relations to make this leap. Our A value then is 0.973. Then we've got our UN. The B value is always going to be some constant value, and in this case it's the number of mice that they release in addition. So that's going to be plus 30. So the A value here then, just to actually state it, would be 0.973. That's coming from the percentage change. And then the b value is this constant value, which is 30. Okay, so not a huge amount of work there, just a bit of interpretation. The same with the second part. So part B, the first part of part B, they're asking the question whether or not the population of mice will stabilize in the long term. Well, remember this recurrence relation, or any recurrence relation, just generates a sequence of numbers. That sequence of numbers can tend towards a limit, like a limiting value, the highest or the lowest it will ever get to, or it can just keep going up or keep going down forever. If the mouse population is going to stabilize, that means it doesn't carry on forever. So the interpretation is that if it's going to stabilize, then that would imply that there's going to be a limit to the recurrence relation. This is our recurrence relation here. How do we tell if it's got a limit? Well, we tell by the a value, the multiplier value. If the multiplier value lies between -1 and 1, which our value does, this is between -1 and 1, then that means that there is a limit. So because that value lies between -1 and 1, that tells you there's a limit. And in this question, a limit, the interpretation of that is that the mouse population never gets beyond that limit, that number of mice. So therefore it does stabilize in the long term. And the limit is the long-term behavior. So we don't know how long the long term is. It's just over time, not like in the short term. Okay, so part 2 of part B, calculate the long-term population. So what is that long-term population? Well, long-term population is the limit. That is the limiting value. So you just need to know the formula for limit, which is not in the formula sheet, which for a general recurrence relation is b over 1 minus a. So this value divided by 1 minus this value. So we've got those values. So we can just plug them in. So our b value is 30. 1 minus our a value, 0.973. Remember, these are calculator questions, or in this case, it's a calculator question. So if we plug that all in to the calculator, then we get quite a weird number. We get 1,111 point. I messed that up. That should have been a point. I'll rub it out with my finger. So 0.111, like this. And then they're asking for this to the nearest 100. So that's just going to be 1100. So this is 1111.111. So to the nearest 100, that's just going to be 1100, like this. So pretty classic recurrence relation question there, really asking you to make the recurrence relation from information, state why there's a limit, or if there is a limit, and then to find that limit. So that is the end of that question. In this question, we've been given the graph of the function g of x, and we're asked to sketch the derivative g dash x. So the key with these questions is to focus on the stationary points. It's a very specific technique, this. So we don't know exactly what this function is. It appears to be some kind of cubic. It doesn't really matter what the function is. You don't need its equation. We just need to focus on the shape and the stationary points. So we've got a stationary point at -2 and 4, and these always become the roots on the derived graph. Remember, the vertical axis on your derived graph is no longer y, it's now the derivative. So g dash x in this case. So because the stationary points have got a 0 derivative, the derivative is 0 at the stationary points, in other words, the tangent lines would go horizontal, that means that they're going to be on the x-axis here because the x-axis represents all of the 0 derivatives. So anything along the x-axis has got a 0 derivative, anything above it has got a positive derivative, so these would all be positive values. Anything below the x-axis is going to have a negative derivative. So let's start by remapping these points over to here. So -2 is going to be like somewhere here, +4 is going to be here. So that's always the first thing to do in these questions, turn the stationary points into roots on this graph. And then we've just got to think about the shape. So in this part of the graph, so to the left of that stationary point, the graph is sloping up the way. That means that the derivative or the gradient would be positive. Between the two stationary points, the graph is sloping down the way. That means that the derivative or the gradient is negative. And then back here, it's going positive again. So I like to personally go straight to the two stationary points and look at the shape between them, so a negative derivative, negative slope, negative gradient, the negatives over in this graph are the points underneath the x-axis. So between the two stationary points, this one, remember, is -2 and this one is at 4. The graph needs to be underneath the x-axis, all negative values, because it's all negative slope between the stationary points there. That means that the graph is going to go something like this. To the left of this point and to the right of that point, the derivative or the gradient goes positive because the graph is sloping up. That means that to the left and to the right of those points on this graph, it's got to be above the x-axis. So in other words, the graph has to come down like somewhere here, and it has to be like somewhere up there. And this is just a rough sketch, but it would be approximately like that. So notice what's basically happened. We've got a parabola graph, which would be some kind of x squared function. We don't know what kind of function this is, but you can tell from the shape that this would be some kind of cubic function. So we don't know exactly the formula, but it would contain an x cubed term. This one, we don't know the formula, but it would contain an x squared term. And if you think about the fact that this is a derivative graph, that makes sense. Because when you differentiate, a power of 3 goes down to a power of 2. So you should always expect a shape of graph which is one order less than the original graph. So a cubic will turn into a quadratic. If this was a quadratic, it would turn into a straight line and that sort of thing. So that's the answer for that problem. We've been given this trigonometric expression and we're asked to write it in the form k cos x plus a. So classic wave function question, this one. So I'd recommend just setting this equal to the thing you're trying to make it equal to. So k cos x plus a in this case. And these questions really are just an application of the addition formula. This is in the format to use the addition formula. So we're going to expand this, just copying the formula sheet. So this would become k cos x cos a. Remember that for the cosine expansion, the plus turns into a minus, and then k sine a sine x or sine x sine a. The order of these two doesn't really matter. Spinning these around, I would recommend to put the a term first, so making this k cos a and then cos x, and the same with the other one. Well, the other one's actually good to go already. That's just because x is our variable here, so it's better to have the variable second. You know, if we write algebra, we write things like 5x, don't we? We don't write x5. So to me anyway, it makes sense to put the x term second. And the other reason for that is helpful for matching up the left and the right hand sides, as we're going to have to do in a moment. So I'm just going to pull down the original expression here. So then we're just comparing the left and the right hand side of the equation. So the thing that goes with the cos x here is k cos a. The thing that goes with the cos x here is 2. So just matching those up to make a little mini equation. So we get k cos a equals 2. Doing the same with the signs. So over here we've got minus negative k sine a. So the negative is super important in this question. You've got to be really careful with those. And it's negative 3 here. So we're matching up these two terms. So it equals negative 3. Because they both come out to be a negative, but only because they've both come out to be a negative, we can actually just ignore the negative. So just imagine those being back to positive. Okay, so getting these two little equations is kind of the starting point, and then we're just going to go through the process to get the k value and the a value, which is ultimately what we're trying to solve for. So the k value is basically based on Pythagoras. We don't need the derivation of where it comes from in the question, in the solution, but just the square root of these two numbers squared added together. So basically these two numbers are forming the short sides of a right angle triangle, and the k value is the long side. But you don't need to worry about the geometry, you just need to know the sort of formula. So that's going to be the square root of 13. Okay, so moving on, we're now going to divide the sine equation by the cos equation. Hopefully this is familiar to you. So sine divided by cos gives you tan. So tan A becomes 3 over 2. So basically the formula sine over cos is tan, and just dividing the sine number by the cos number. Again, you don't need the derivation of that in your solution, you just need to present that like this. This is a calculator question, so to get our a value, we're going to take the inverse tan of 3 over 2. Should probably do a cast diagram at this point. The cast diagrams are more important when one of these numbers is a negative. You kind of don't need it if they're both positive, but we'll do it anyway just to show where that comes from. So remember, you're taking the cast diagram off of these two equations, not from the tan equation. So the first equation is cosine positive, so that would be a check mark here and here. Then the second equation is sign positive, that will be a check mark here and here. The one with the double tick, the double check, that's going to be the quadrant where the A value should be. So this is the first quadrant between 0 and 90 degrees. And this would just need to be put in the calculator. So when you do that, which I did already, this comes out to be 56.3 degrees. And that's basically our solution because we've now got the K value and the A value, and that's what we set out to achieve. So I would just recommend writing the original line again, just to tie it all together. So we've got 2 cos x minus 3 sine x, and that is equal to the K value, which is root 13, cos in this case, and then x plus the A value, 56.3 degrees. So very, very procedural, these questions. You just need to know the process, but really just an application of those addition formula expansions. Part B of these wave function questions always involve part A's solution, the answer from part A. So in this case, we're being asked to solve an equation, but this equation is unsolvable in that form. You can't solve this equation with the mix of sine and cosine in this particular format. So we're just going to say, well, that thing there, 2 cos x minus 3 sine x, is the same as this thing. So if we swap that into there, hopefully that will then be an equation which is solvable. So just using the solution from part A, just to rewrite this term, or these terms. Okay, and that gives us a trig equation to solve. Not necessarily easy, but it is a trig equation which we can solve. So just dividing the root 13 over to the other side, we're going to go like this. And I would recommend a cast diagram at this point. So cast diagrams aren't necessarily mandatory, but they're good for just getting the orientation as to where the solutions are going to be. So remember, this cast diagram is going to be in degrees. We're working this question in degrees. All we care about at this point is cosine positive value. So checking the two positive cosine quadrants. So we're looking for solutions between 0 and 90, and then between 270 and 360. So the first quadrant, 0 to 90, fourth quadrant, 270 to 360 degrees. But we've got to be mindful of this horizontal shift here, and we'll deal with that later on. There's a bunch of ways to approach a problem like this. I'm going to show you my method. So I would recommend just taking the cosine inverse as normal. So just take inverse cos of the number over here, which is 3 over root 13, which I have forgotten to do. So I'm going to grab my phone calculator and just put that in. So that's not an exact value, so you wouldn't be expected to do that manually. You can use the calculator for that. Okay, so this comes out to be 33.7 degrees. So that 33.7 is not a final answer. It's not a solution for x. It's a solution, if you like, for x plus 56.3. So let me just pull that down here. But notice that at 33.7, that's the check, that's the solution in this quadrant. So we get x plus 56.3 is equal to 33.7. If we go ahead and solve that for x, that's then going to be 33.7 minus 56.3. So let me just do that, 33.7 minus 56.3, so it comes out to be negative 22.6. That is a solution, but it's outside the range of valid solutions. It's not in the range 0 to 360. This number would satisfy the equation, but it's not allowed, so we're not going to include that as a solution. So what do we do from there? Well, let's work up the next solution, which would be this one here. We're going to get this one here by doing 360 minus the first solution. But again, that's not a solution for x, that is for x plus 56.3. So all we're doing is substituting the x plus 56.3 as though this had been like just an x in here. We would be doing the same thing if it was just an x in there. So this is going to be 360 minus 33.7. So we'll just go ahead and compute that. 360 minus 33.7. Probably didn't really need the calculator for that one. But anyway, fair enough. So that's 326.3 degrees. So again, that's not our final answer because we still need to adjust here. So x is going to equal 326.3 minus 56.3. And just quickly check that. So minus 56.3. So it comes out to be 270 degrees. That is in the correct range. So that is going to be acceptable. This one, not so much. This one is okay. With these left to right shifts, so you've got to think, are there any potential other solutions? Well, if you think about a cosine graph and a sine graph, it's got a period of 360 degrees. So that's like one cycle of the graph, but the next cycle goes like this. So if you were a point on the graph, say here, then that point is going to recur again over here, and then again over here, and again over here, and the same back the way. And the distance between those recurring points is the period, 360 degrees. That's what the period means. So this solution here wasn't valid, but if we take that solution and add on, so that minus 22.6, if we add on the period, 360, that will give us another valid solution. So 360 minus 22.6, again, should be able to do that without a calculator, but hey, it's a calculator question, so may as well use the calculator. So 337.4 degrees. Those second solutions with horizontal shifts can be tricky. You've just got to think about, are any of the solutions going to get like sucked into the range by this shift or by the fact that the period is 360 degrees. So this here and this here are the two valid solutions to that equation. In the first part of this question, we've been asked to write this trinomial into completed square form. So very procedural method required for this. So we start by identifying the numerical common factor between these two terms. So these should have a common factor which is not shared by the third term. That's how these questions tend to go. So the common factor there is 6 or negative 6. So I would recommend using negative 6. In fact, you can see in the question that they want you to use the negative by the form they've recommended. So this is just going to be just the numerical common factor. We're not going to include the x in that. That's just part of the process. And you probably want to use a square bracket for this. So this would then be x squared minus 4x inside. Be careful with that because negative 6 times negative 4x would be positive 24x. And just leave the negative 25 on the end there. Okay, so that's not completing the square, that is just pulling out a common factor. Now we're going to complete the square on the inside of the square bracket. So we go x minus the half of this number, so it's always half of the coefficient of the x term, so the number in front of the x term. So x at minus 2 in this case, put your squared on the bracket. So that's just part of the process. Whatever number you've just put in the bracket, minus 2 in this case, square that number. Minus 2 all squared is 4, and then take that away. So you're always doing that, taking away the number you've just put in the bracket squared. That's just part of the procedure. Leave the minus 25 on the end. There's different ways to do this technique, but this is the way that I would recommend. And then multiplying the negative 6 into the square bracket. So negative 6 times this first term, which is the round bracket. Well, you can't multiply that into the round bracket. So we're just going to park it in front of it like that. Okay, so that's just negative 6 times this term. Then negative 6 times negative 4 is plus positive 24. And then taken away from that, the 25. So we end up here with negative 6 bracket x minus 2 all squared. 24 minus 25 is minus 1. Okay, so that is a completed square form. Pretty common technique, not always easy, but just got to do it step by step really carefully. Don't try and cheat it. Don't try and jump straight from there to there. Just too difficult. It's just likely to go wrong. Okay, so initially part B of this question looks very unrelated to part A. In part B, they're asking us to show that this function, which doesn't have any direct, obvious correlation to this, but there must be a link between them, you would think. We're being asked to show that it's strictly increasing. Strictly increasing really means the graph is always going up the way. So graph going up the way means positive gradient. Gradient derivative are essentially the same thing. So that's really saying, hey, can you show that this function is always going to have a positive gradient? Positive derivative, gradient derivative, same thing. So let's maybe start by working up the derivative. So f dash x, just using the power rule, this becomes negative 6x squared plus 24x minus 25. The 9 disappears, goes to 0, and then you can see that that is now turned into this here. So that's directly the link between the two parts of the question. So we want to show that this is always greater than 0. That's what we're trying to establish, that the derivative which is just another way of thinking of the gradient, is always strictly greater than 0. So just going to put that in there as a note. That's what we're aiming for. So somehow we're going to have to show that this is always greater than 0. So just going back to our derivative, f dash x, well, we now know that this here can be written like this here. So just changing it to that completed square form. So negative 6 bracket x minus 2 all squared, x minus 2 all squared minus 1. Now, how does that help us? We're trying to show that this is always strictly, oh, I'm sorry, it's strictly decreasing, this question, not strictly increasing. So I got that the wrong way around. So let's just back up for a moment. So strictly decreasing means that the gradient is always going, the graph is always sloping down the way, the gradient is always negative. Derivative, therefore, should always be negative. So we're trying to show that the derivative of this function is always less than 0. Okay, so how can we show that this here, which is just another way of writing the derivative, is always less than 0? Well, if you think about it, it doesn't matter what number you put in here for x. This here is getting squared. If you square any number, whether it's positive or negative, it's always going to be negative. So we can definitely say for sure that x minus 2 squared is always going to be greater than or equal to 0. If the x was 2, 2 minus 2 is 0, 0 squared is 0, so it could be equal to 0, otherwise it's going to be greater than 0. For example, if this was minus 2, minus 2 minus 2 is minus 4, but minus 4 all squared is positive 16, so this is always going to be greater than or equal to 0. That means then that if you take something which is always positive or greater than positive or equal to 0, this thing here, and multiply it by negative 6, well, that is then going to be 0 or a negative number, because if this is 0 times negative 6, it will be 0. If it's a positive number times negative 6, it will be some negative number. So it has to be negative or 0. And then though, we're taking away minus 1. So if it's 0, take away minus 1, that's going to be minus 1. If it's already a negative, take away minus 1, it's going to be more negative. So by that logic, we've established that the derivative f dash x, this thing here, is always going to be strictly less than 0. And that therefore implies that f of x is always going to be strictly decreasing. In other words, the derivative or the gradient is always going to be less than 0. In this question, we've been given this kind of odd looking function f of x, which is the cube root of x plus 8, and we're also told that the domain of the function is 1 to 1000. So that means that this function is valid for x values between 1 and 1000. And in the first part of the question, we're asked to find the inverse f to the minus 1 of x of this function. So pretty standard technique, this one. So we're just going to take the function f of x. In fact, let me just quickly rewrite it down here. So f of x equals the cube root of x plus 8. And we're going to swap out the f of x for a y. That's just because we're going to do some algebra, and we don't really use the f of x function notation in algebra, so swapping it out like that. And basically the goal with these questions is then to just change the subject of the formula to x. So we're going to do that by subtracting 8 from both sides to get y minus 8 equals the cube root of x. To get rid of a cube root, we need to cube both sides. Because we've got two terms here on the left hand side, we're going to have to put that in a bracket, y minus 8 all cubed. Cubing the right hand side just gets rid of the cube root, that leaves you with x. You could spin that around if you like to make x a subject on the left. So x equals y minus 8 all cubed. Remember, our function was given in terms of f, so we need to put it back into that notation. So the final answer would be that f to the minus 1 of x is just this thing here, but with the x swapped in for y. So it's going to be x minus 8 all cubed. And you can kind of see that this looks to be the kind of opposite of this here. So a plus 8 becomes a minus 8, a cube root becomes a cube. That should always be the case for inverse functions. You can see almost by inspection if the answer looks reasonable. So part B of the question is a little tricky, not something you probably spent a lot of time on, but we're asked basically to find the domain of this function. So we're trying to find the domain of the inverse function, so the domain of f to the minus 1 of x, the domain of the inverse function, without going into too much detail, is equal to the range of the original function. Okay, so that's equal to the range of the original function f of x. So remember, domain really just is a fancy word. It basically just means all the values you're allowed to put into the function without there being some issue. And the range is all the values that you get out of the function once you put those domain values into the function. So for a lot of functions, the domain and the range are all numbers, all real numbers. Sometimes they're restricted. So here the domain for the original function is 1 to 1000. But what we're trying to do is to figure out the range of the original function. But the range is just what we get if we take the endpoints of the domain and put them into the function. So basically, if we take f and evaluate it at 1, we're going to get the cube root of 1 plus 8. So cube root of 1 is 1 plus 8 is 9. If we do the same thing for the endpoint, so evaluate the function f at 1000, then we're going to get, remember this is a calculator question, so cube root of 1000 plus 8, the cube root of 1000 is 10, 10 times 10 times 10 gives you 1000, so that's going to be 10 plus 8, which is 18. So what does that tell us? Well, that tells us that the range of the original function, the values you get out of that function for that domain, is going to go between 9 and 18. But the range of that function is equal to the domain of f to the minus 1. So that tells us that the domain of f to the minus 1 of x is all the x values between 9, so less than 9, greater than or equal, no, x greater than or equal to 9, less than or equal to 18. Not a very common question that, I mean, domain questions are common, but in this question you're being asked to find the domain of an inverse function, which basically you've got to do by finding the range of the original function. So slightly more into the realm of problem solving, that one. So we're given this equation which gives us a power at time t based on this sort of formula, so 120e, so this exponential term, to the power of minus 0.0079t. So quite an ugly looking thing. I think it's always important in these questions to take a moment to just think about what does this actually mean. So again, it's just saying that the power is given at time t by basically plugging a t value in there and then working out what that would come out to be. So it gives you the power at time t. In the first part of the question, we want to know what is the power initially. So look out for keywords in questions like this. So initially, or they might say something like at the beginning or at the start or something like that. But initially basically means that you've got a t value of 0. So we're just going to be subbing in a t value of 0. So that's going to be p sub 0. So this is a subscript. So the subscript is 0, p sub 0. So that equals 120e, keeping everything the same apart from the t value, which we're going to be making to 0. So it's this number here times 0. Okay, but that whole sort of power there is just going to become 0. So this becomes 120 e to the power of 0. Now this is a calculator question, but anything to the power of 0 is 1. So this is really just 120 times 1. So just 120. I think this was in watts, so it's be 120 watts would be the power at the initial stage, so at time 0. So pretty common first part of a question like this to work out the initial value. In part B, they're asking how long would it take for there to be a 15% reduction in power. So if you take 15% away from something, if you reduce something by 15%, you're left with 85%. Okay, so if we want to take that initial value, which is 120 watts, that's the initial power, and work out a 15% reduction in that, then we're going to achieve that by multiplying it by 0.85. Or you could multiply it by 0.15 and then take that number away from 120. It's more efficient just to multiply it by the number decimal 0.85. So if you do that again, that would need to be put into the calculator. I did it already, and that comes out to be 102. So how do we use that? Well, we want to then substitute that 102 into the power position in our formula. So we're going to replace our p sub t value with 102. So we're saying that this is the power this is the power we're interested in, and we want to calculate the time value. That's what we're after this time, that would give us that power value. So keeping everything else the same, remember that 120 is a constant, that'll never change, and this becomes then e to the minus 0.0079t. It's a bit of a cumbersome number. And then this is really now turned into a log exponential equation. We're trying to solve for t. T is currently like locked up there in the power. We need to get it out of the power, and there's quite a definite process for that. So first of all, simplifying by dividing both sides by 120. So we're going to get 102 divided by 120. So that's just normal sort of equation work, leaving us with this e term, which is a little bit cumbersome to write. Basically, now we're going to take the log to base e, which we can shorthand as ln. So remember that this, I'll just put it here. So that this terminology that we use, so ln x, is just shorthand for log to base e of x. So it's always important, I think, to keep that in mind. I know it appears just as a button on the calculator, but that's what it actually means, log to base e. So we're taking this ln of both sides, so log to base e of this, so ln 102 divided by 120. And then you can write this in if you wish. I'm just going to write it in to show you. So ln of e to the minus 0.0079t like this. Okay, and then basically all that's going to happen here is, so all that we've done there actually is just to put an ln here and an ln here, doing the same thing to both sides of an equation. You're always allowed to do that. But if you get, the way this basically works, if you imagine that there, I'll just pull this up here just to quickly explain this. So if you had log, if I wrote that as log to base e, it would be log to base e of e to the minus 0.0079t. But remember, there's one of the log rules that says if you've got this scenario, you can bring the power in front. So if we bring the power in front, we would get negative 0.0079t times log to base e of e, but log to base e of e, log to base a of a, log to base anything of itself is just 1. So this just becomes 1, and you end up with just that thing there. You don't need that working, but just to show why, on the next line, the log and the e will just cancel, and you'll end up with just minus 0.0079t. Wow, it feels like I've written that number 100 times already. Okay, and then just leaving this side alone. Keep in mind that you're trying to solve for t, so we just need to divide both sides now by this number. So yeah, a little bit ugly. T is going to come out to be ln 102 divided by 120. And I might just use a divide sign here actually, so it's going to be divided by minus 0.079. And I did that earlier. I'm going to refer to my cheat sheet, and that came out to be 20.57. So 20.57, the time is given in years. So it's going to take 20.57 years apparently for the power to be reduced by 15%, or in other words, to take the power down to 102 watts. So that's the solution for that question. In part A of this question, we're trying to show that x plus 3 is a factor of this polynomial. So typical polynomial question, but normally these functions are cubics, not quartics like this one. So that should be the first thing that kind of flags up in your brain, like what is going on there. But it's still the same process. It's going to be synthetic division. So we're trying to divide this by x minus 3. So we're going to use a synthetic division table. Doesn't matter what the power, the highest power called the order is, you can always use the synthetic division table, but it might just look a little bit different. It's going to have more terms in this case. So making sure that you've got all the terms, so that's the 3 and then the 10, making sure you're not skipping a term. So we've got a power of 4, 3, 2, 1 and 0. If there was a missing term there, you would need to put a 0 in the table. We've got them all, so that's fine. So 3, 10, this one is a 1, and then negative 8, and then a negative 6. So because it's an x minus 3 factor, we're going to have to use, oh sorry, it's actually an x plus 3 factor. So we're going to put minus 3 outside our table. So remember, that number will always be the number which would make this 0 if you were to put it in the x position. So minus 3 plus 3 is 0. So basically always using the opposite number there. So pulling down the first number, which is the 3, like this, multiplying these together. So you should be familiar with this technique. Adding these, so 10 minus 9 is positive 1. Multiplying that to the outside number to give us a minus 3. Adding these together. So some people like to put a plus in here just to remind them that they're adding 1 plus minus 3 is like 1 minus 3, which is negative 2. Multiplying these together again to give us a positive 6. Adding these guys, that would give us a minus 2. Multiplying these together again to give us again a positive 6, and we're going to be adding these. And we've got what we hoped we would achieve, which is a 0. If you get the 0 remainder, that shows that it's a factor. So you could just say something like, therefore, since the remainder equals 0, x plus 3 is a factor. Or you can use your own language for that, but make sure you get in something about the remainder being 0. That's the only reason why it's a factor, because the remainder is 0. If the remainder is 0, it's a factor, and if it's a factor, the remainder is 0. That goes both ways. Okay, so that's the first part of this question. In part B, we're asked to fully factorize. So remember, the way these work is that once you've confirmed that the first term is a factor, then we can use that as one of our factors. And the other factors are going to come from this part here in the synthetic division table, which is the quotient. Now normally there's only 3 terms here. If you're dealing with a cubic function, we've got 4. So this is going to be 3x squared, no, cubed, plus 1x squared, etc. So the next factor will be 3x cubed plus 1x squared, or just x squared, minus 2x, and then the constant minus 2. Normally when you do these with a cubic function, at this point you would have a trinomial in here, so something like that, a quadratic expression, and you can directly factorize that into 2 more brackets. You can't directly factorize a cubic. That means that if this does factorize further, we're going to have to do synthetic division on that as well. So setting up our synthetic division table just for this bit here, okay? So that would look like just putting in the coefficient numbers, 3, 1, minus 2, and minus 2. So 3, 1, minus 2, and minus 2. But the difference this time, we don't know what one of the factors is. So this requires you to use a slightly different technique. Over here, we knew it was a x plus 3 we were working with, so we put a minus 3 outside the table. We don't know what we're using this time. But the trick is, the key is that the number you use has to divide into this n number. So it could be 1, 2, minus 1, or minus 2. Potentially you might need to try all of those. 1 is always a good bet to check because it's the easiest one to work with. And you can actually just check it real quick by putting 1 into here. And if it comes to 0, then it's going to come to 0 here as well. So you don't necessarily need to do the synthetic division table. If you do need to do the table, just check them one at a time. And if you have to do multiple tables, fair enough. Keep going until you get to 0. But you can see here that if you put in a 1 for x, well, if you put in a 1 for x, the x's kind of just go straight to 1 if you cube them or square them. So this would be like 3 plus 1, so that's 4, minus 2 times 1, which is 2, so it's 4 minus 2, which is 2. Take away another 2 is 0, so that does come to 0. So that tells us that we can put a 1 outside our table, and then just working through the table to confirm it. So a 3 there, multiply these guys, that becomes a 3, add them, that's a 4. 4 times 1 is 4, add those, that becomes a positive 2. 2 times 1 is 2, add those, and we do indeed get a 0. So that sort of inspection method does sometimes need multiple tables, or just quickly check. But if you're going to try multiple numbers, try 1 first. 1's always a good bet. And in questions like this, they're not going to give you a hideous n number. Like if that was a 12, you'd have to try like 1 and 2 and minus 1 and minus 2 and 3 and 4 and 6 and all sorts of numbers. But normally it's going to be 1 or minus 1 or maybe 2 at the most. So what does that tell us? Well, that tells us we can update this now, because now we know that the first factor, x plus 3, is still going to be there. This now shows that x minus 1 is a factor, because remember, if it's a plus 1 there, the factor would be minus 1. And now we've got this trinomial, which is 3x squared plus 4x plus 2. Now remember, these don't always go all the way down to 4 or 3 brackets. You know, like if you're doing a cubic, it will usually go to 3 brackets, but it doesn't always. if it's a quartic, you would expect that it could go, well, it certainly could go to 4 brackets, but it doesn't have to. So the order of the polynomial, which is the highest power, which is 4 in this case, that's the maximum number of brackets you're going to get in your factorized form, but it's not the number you're necessarily going to get. So we know that it could end up being 4 brackets. At the moment we've got 1, 2, 3. And does this factorize? Well, it doesn't look like, well, it's definitely not going to factorize. You could play around with 2 brackets there, but there's nothing you could find to factorize that into 2 brackets. So that there is the final full factorized form. So these optimization questions where you're asked to make the equation are not always easy. They need a little bit of creativity and experience, and this one is particularly challenging. So we're being asked to show that the surface area equals the equation that they've given us. Remember, that's not going to be your starting point, that's going to be your end point. You've got to start somewhere else and get to that point. So just ask yourself, like, what are we dealing with here? Well, we're dealing with area. Sometimes it's volume, sometimes it's something else. This time we're dealing with area, so we're just going to have to start making the surface area. So I've not attempted to draw the diagram. I'm just going to be working off a diagram I've got over here. So we're going to have to break this one down into the various parts of the shape. So let's maybe start with the top part and the base. So the top part and the base are going to be the same. Okay, so we're going to work the different parts of the shape individually, and then we'll add them all together, and then hopefully that will get us close to what we're looking for. So if we look at the shape, the top part it's a square, so it's going to be 3x times 3x, but then minus the bit in the middle, because we're like cutting out that x shape in the middle. So it's going to be 3x times 3x, which would be 3x all squared. So we've got 3x all squared. So that would give you basically the area if it was just a square. And we're subtracting from that the bit for the tunnel, which is x times x, which is x squared. So it's going to be like that. Okay. If you multiply this out, that's going to be, so it's 3x all squared, which is 9x squared, minus x squared, and that comes out to be 8x squared. Okay, so that would be the top or the base, but we need to multiply that by 2. So that means that in total there, well, let me just maybe write it there. So in total there, that's then going to be 2 times that, or 16x squared. So that deals with the top and the base. So let's have a look at the sides. The sides, I think, are a little easier because there's no subtraction there. They're just basically sort of rectangles. So the sides are going to be 3x times h, and there's 4 of them. So we've got, basically, we can go straight to the answer here, I think. So it's 4 times 3x, let's put that in a bracket to keep it clear, times h. So that's just going to be 12xh. Okay, that's for the sides. And then finally, we've got to then do the tunnel, because we're dealing with surface area and we need to accommodate all of the surface areas, including the tunnel. So the surface area of the tunnel, well, it's basically made up from 4 rectangles, isn't it? And each of the rectangles has an area of xh, just using basic geometry like length times breadth. So it's xh times 4, or 4xh, like that. Okay, so what does that give us? Well, that gives us a total, so total surface area, which is equal to these guys all added together. So we've got 16x squared, and then we're adding to that 12xh, and we're adding to that 4xh, combining the terms that we can. So we've only got one x squared term. These two are the same, so they're both xh terms, so that will become 16xh. Now that's pretty close to the formula, but if you look at the formula, it's got the 16x squared term, but it doesn't have this second term, and that's always pretty much what happens in these optimization part A questions where you're making the formula. This is a function of 2 variables. We only want it to be a function of 1 variable, x, so we need to somehow get rid of that h term. So that's going to be our sort of challenge now, and that's always to do with the additional information that's given in the question, which in this case is to do with volume. It's telling us that the volume of that box is 2,000 cubic centimeters. So if you think about it, the volume we can get by basic geometry, so length times breadth times height. So imagine the box didn't have the tunnel in the middle, it would just then be a cuboid, so length times breadth times height. And just looking at what those actual dimensions are, so if we call that 3x times h, so that would be, I'll just put it in brackets to keep them clear again, 3x times 3x times h, so that's going to be 9x squared h. So that would be the volume if there was no tunnel. The volume of the tunnel itself is x times x times h, so x squared h. So let me just maybe use like a subscript here to mean tunnel or something. So that's just going to be, well, it's the same thing as length times breadth times height for basically a cuboid, which is the tunnel. And that's going to be, depending on how you think about it, that's going to be x times x times h, which is x squared h. So tricky, right? It's tricky. There's a lot of stuff going on in this question. So this would be the overall volume of the box if there was no tunnel. This is the volume of the tunnel. So we need to subtract that from this one here. So, so let me just say, well, I don't know how to subscript this. Let's say this is the volume of the box without there being a tunnel. So the overall volume, let's just call that V to keep our things nice and separate. That's going to be 9x squared h minus x squared h, which gives us 8x squared h. But this is a formula for the volume based on x and h, but we know the volume is 2000 cubic centimeters. So this then implies that this x squared h, this expression for the volume is equal numerically to 2000. And what do we actually want to do here? Well, what we want to do is to get rid of this h term. There's no h term in the formula, so we want to change the subject of the formula to h. So that's going to be 2000 divided by 8x squared. And again, I know this is not easy, and that would simplify down to give us 2. So 2000 divided by 8 is 250. So this would give us 250 over x squared. So this work in here was to get us the total surface area, and this is fine, this is the surface area, but it's a mixture of two variables, x and h. This part here is basically side working to work up the volume to get a formula that connects x and h. What we're now going to do is substitute this result back into here. In other words, we're going to swap out this h term for that guy there. So let me just find some space to do that. Well, I'll just pick up that down here. So that tells us that the surface area, which is, we'll call that A, is 16x squared plus 16x times our new version of h, if you like, which is 250 over x squared. So you're kind of merging your two separate pieces of work in, which again, I appreciate is not easy. This is a calculator question. If you multiply the 16 and the 250, you'll get 4,000. So this becomes 16x squared plus 4,000. You've got an x on the top, an x squared on the bottom. You could divide top and bottom by x, and you would end up with just an x down there. So tricky, but that's how you get to the formula from the information in the question. In part B of this question, we're asked to find the minimum value of a. So that basically means try to find the minimum value of this function. To find minimum values, we approach it like a stationary point question. So we're just going to take the derivative and set it equal to 0. That's how you find maximum and minimum critical points on a function, and that's what we're going to do here. So we're going to take our derivative. So you could notate that as a dash x or dA dx. So I'm going to go for dA dx this time. And just scanning across our function, is it in a differentiable form? The first term is fine, the second term not so much. So we need to put that in a form in which we can use the power rule in this case. So 16x squared will just leave the x term on the bottom here, comes up to the top to make it an x to the power of minus 1, because remember this is an x to the 1. Secretly there becomes an x to the minus 1 on the top. That is now in a differentiable form. So we can go ahead and take our derivative using the power rule. So multiply the power in front. So 16 times 2, 32, x to the power of reducing the power by 1. So x to the power of 1. And then minus 4,000 x to the minus 2. So it's always good practice if you take a derivative, not only in this type of question, any question, if it comes out to be a negative power, put it back into the form of a positive power, which you can do just by the reverse of this rule here. So that stays as 32x minus 4,000 over x squared. So if this was a stationary point question, you would probably write in a line of explanation where you would say something like 4 stationary points, dy dx or f dash x equals 0. Kind of want to do something similar here. Question is not strictly stationary points, so I'm going to write for minimum, for minimum surface area, because that's what the formula represents. For minimum surface area, dA dx, which is the appropriate letters, I guess, for the question, equals 0. So that's what we're going to be doing, taking our derivative and setting it equal to 0. So I'm just going to pull that over here. In fact, to make some space, we'll maybe just put it here. So we've got our derivative, 32x minus this form here, which is 4,000 over x squared. And we're going to set that equal to 0. If we can then solve that, that will give us the key point, or points, the x values that either maximize or minimize the function. So let's start by getting rid of the fraction by multiplying all the terms by the denominator x squared. So 32x times x squared is 32x cubed, and then minus 4,000 equals 0. The 0 is also getting multiplied by x squared, but that would just stay as a 0. And then basically we just need to solve this equation from here. So how do we want to do that? Well, in this case, I think we should take the 4,000 to the other side. So 32x cubed equals 4,000. And it should always be in a question like this, when you get to this point, you would expect these numbers to divide down to quite a friendly number. In this case, if we divide them down, they come down to, using a calculator, to 125. And not only is it good to get a whole number there, if you get some dodgy looking decimal number, it's probably wrong, but you should also be thinking ahead, well, is this number cube rootable? Because we're going to have to take the cube root. If this was a squared, you'd have to take the square root. If it's like a square root and this is not a square number, it could be right, but you would probably expect the question to be designed to come out to be a whole number. So that's a clue that it might be correct. So in this question, we're given this relationship between the variables a, b, x, and y. And we're also given a straight line graph, which has got a vertical axis, which has got a log on it. And somehow we've got to piece that all together and figure out the a and the b values. So they're kind of weird questions, these. They're not very popular with students. And they've kind of got a bit of a method, but you've got to sort of adapt it a little bit on the fly. So what we're going to do here is start by using some of our log rules. So if you look in the question, you can see that the log is to base 4. So we're just going to take the log to base 4 of both sides of this expression. So because it's an equation, you can always do the same thing to both sides, including introducing a logarithm. So we're literally just going to go, okay, so log to base 4 of y must equal log to base 4 of the other side. I'm just going to pop that in a bracket, so ab to the power of x. And now we can sort of use one of our log rules to separate this and to make it log to base 4. This is a product, so it's log to base 4 of a plus log to base 4 of b to the x. I'm just going to maybe pull down the left-hand side here as well. And again, so log to base 4 of y equals this guy here. So the log to base 4 of a term, we're just going to leave. Always look and see which of your log rules you can use. Here we've got a power, so we can bring the power in front. So that becomes x log to base 4 of b. And what you're basically looking for in these questions is to turn this original expression into something that looks like the equation of a straight line. So the equation of a straight line, remember, is y equals mx plus c. But in the case of our graph, it's not just a y, it's a log to base 4 of y for the vertical axis. So the log, in this case, this weird log straight line graph, the equation would be log to base 4 of y equals mx plus c, because the x, the horizontal axis, is just a normal horizontal axis, so it stays as an x. So if you compare what we've got here to what we've got here, they're kind of close. We just need to sort of reorder these terms. So the left-hand side is log to base 4 of y, so we can keep that. This here needs to go in this position, the first position. but the x needs to be in front, behind the coefficient. So this here, log to base 4 of b is going to go like that, and I'm just going to put that in a wee bracket, and that's going to go in front of the x, and then we're just going to put this term log to base 4 of a onto the end. So this basically now looks like the equation of a straight line for this particular graph where we've got that weird log vertical axis. So y vertical axis equals m gradient x plus c y intercept. Okay, so what do we do with that? Well, basically this here, this guy here, is playing the role of the gradient. And this guy here, just by the position in the equation, is playing the role of the y-intercept. So what is a gradient and what is a y-intercept? Well, the gradient we can get by the 2 points they've given to us on the line. So let's just say, we'll just call that m for a gradient, just using the normal gradient formula. So it's 8 minus 1 divided by 3 minus 0. So it's just going to be 3. 8 minus 1 is 8 plus 1. So it's going to be 9 divided by 3, which is 3. And if you look at the line, which I'm just checking on the screen here, it is quite steep, so that gradient of 3 looks to be good. Okay, so we'll just park that for the time being, and then the y-intercept, which you can call the c value. Well, the y-intercept is given in the question because that point 0 minus 1, that is a y-intercept. So we can say that the c value should be at minus 1. So how does that help us? Well, we know that this expression here is the gradient. So we can say then that log to base 4 of b, and remember in this question, ultimately we're trying to find the a and the b value. So log to base 4 of b, this is playing the role of the gradient, this is a gradient, but that is a gradient 3 numerically, so those two things must be equal. So that gives us that, and basically that has now given us a little log equation to solve to get the b value. You solve this by rearranging it as an exponential, so you take the base number, which is 4, keep that as the base on your exponential. In other words, it's the thing that's going to have the power on it, and you just flip these two terms around. That doesn't need to go there. So that's going to be 4 to the power of 3 equals b. 4 to the power of 3, this is a calculator question, but 4 cubed is 64. So that tells you that b equals 64. Okay, so a little bit weird, right? Not exactly, well, yeah, just a little bit weird. Not something that you see every day. So the y-intercept is being played by log to base 4 of a. It's in the position to play the role of the y-intercept. So we can say that log to base 4 of a is equal to the y-intercept, which we identified to be minus 1. So just doing exactly the same thing as we did here, solving this little equation by a rearrangement. So that's going to be 4 to the power of minus 1 equals a. 4 to the power of minus 1 is 1 over 4, or otherwise known as 1/4. So these questions are strange, they're icky, students tend to not like them very much. I'm not a huge fan of them either, to be honest, but that's basically the technique. Just remember that the key is to use your log properties to get the original thing into the form of a straight line. Then you've got to use the information in the question. Sometimes it's the vertical axis, it's the log, sometimes the horizontal, sometimes both. So that's why you've got to kind of adapt these a little bit on the fly. The key to unlocking this question is to be familiar with the terminology, rate of change. Rate of change is code for derivative. So if you ever take a question that says rate of change, just in your head interpret that to mean derivative. So they're telling us that this expression here is the rate of change of some function. That's just another way of saying that is the derivative of the function, the f function in this case. So that means that we can say that not f of x equals that, but f dash x, the derivative, the rate of change, equals that there. That then means that this is turned into a differential equation. Differential equation being an equation which contains a derivative and then the expression. And we're also given this information, the point that's on the original function f of x, and we're going to use that later on. So the question is to find the original function f of x, which would give you this derivative. That's what we're being asked to do. Well, how do we do that? How do we get rid of a derivative? How do we undo this derivative to take it back to its original f of x? Well, we do that by integrating. So if we integrate, integrals remember antiderivatives, the opposite of a derivative. So if we integrate the left-hand side here, we're going to go back to f of x, and that's just going to be equal to the integral of the right-hand side. So the integral of all of this guy here, and we're integrating with respect to x. So this is really an integration question. These are all in the form to use the power rule for integration. So increase the power by 1 divided by the new power. So this would become 3x cubed divided by 3 minus 16x squared divided by 2. And remember that a constant like the number 11 integrates to 11x. That's always the case for a constant. Because this is an indefinite integral with no limits on the integral sign, we need a plus c, which is really important in this question type. Okay, so that's our f of x. Can't we simplify it? Well, these 3's here would cancel to leave us just x cubed. And then 16 divided by 2 is 8. So we're going to get minus 8x squared. The other two terms we're just going to leave alone like this. So let me just pull this up to the other side. I'm also going to swap my pen, which appears to be dying, for a new one. So we've established that f of x is equal to this guy here, and we're almost done at this point. It's just that we want the function which goes through the point given in the question. They're telling us that this f of x function shouldn't just randomly go anywhere on the xy plane, it should go through the point 7, 0. Now this function here would be at different sort of heights, if you like, depending on what the c value is. So at the moment this is a whole family of functions. It's not a function because the c value, the constant of integration, is an arbitrary value. It could be any value you want. So if you were to sketch like a whole bunch of graphs with different c values, this is a cubic function, it would look something like that. But as you change the c value, the graph would be like higher up or lower down, and you would get like a whole family of what are called solution curves. But only one of those curves would go through the point we're interested in. Let's say it's this one here, the point 7, 0. So we're trying to identify that curve, and we're going to identify it because it's going to have a particular c value associated with it. So how do we go about doing this? Well, we just sub the point 7, 0 into our formula, our equation that we've got for f of x. Remember that the 7 obviously is the x, the 0 is the y value, but remember that y and f of x are interchangeable. So when we're plugging in here, 0 is playing the role of f of x and 7 is playing the role of x. So our 0 is going to go on the left hand side. Then we're putting 7 into the right hand side, so we're going to get 7 cubed minus 8 times 7 squared plus 11 times 7 plus c. These are quite high numbers, but it's a calculator question, so we could just calculate that. So I've done this one already. And once you've done the numeracy, you might need a couple of lines of working for that. The c value comes out to be negative 28. So there's no real limit on what that could be. It could be positive, negative, big number, small number, just depends on the question. So that now tells us that the particular function we're looking for is f of x equals all of that stuff up there, x cubed minus 8x squared plus 11x minus 28. Okay, and that's the function that we're looking for. That is the solution to that problem. In this question, we've been asked to find the angle between the vectors u and v. So we've got a formula on the formula sheet that helps us to start to work into that. So it's written with vectors a and b, but just updating it for u and v. So it's to do with the dot product or the scalar product. And it says that if you've got two vectors u and v, if you take their dot product, then that is equal to the magnitude of the vector u, so that's the length or the size of the vector, times the magnitude of vector v, times the cosine of theta, which is the angle between u and v. That's really what we're trying to find in this question, the angle theta. If you rearrange this formula, then you would get cos theta is equal to u dot v divided by the magnitude of u and the magnitude of v. Remember, if you're writing lowercase vector, well, lowercase letters for vectors, you need to put a little line underneath them unless they're in bold. But because you cannot really write in bold, then we need to put little lines under them. That's why I'm doing that. So essentially, to solve this problem, this is the little formula we need to use. So we need to start to figure out these bits. So that's where the information in the question is going to come in. So we've already got the magnitudes of u and v, so that's going to form this part here. This part here we can sometimes make by the other dot product formula that's on the formula sheet, but to do that we would need to know the vectors in component form, which we don't have. Instead, in this question they're giving us this information. So for the time being we don't need this information, we'll use it later on. Let's work with this. So this is the dot product u dot with the vector u plus v. So u plus v is two vectors added together, but that's also a vector. So it's just the dot product of this vector with that vector equals 21. But the way these dot products work, the properties of these dot products are a little bit like normal algebra. Remember, these are not just algebraic letters, variables. These are vectors, but we can expand out this bracket, if you like, by u dot u plus u dot v. Okay, and that is equal to 21. So not easy this, but if you think about this one here, so u dot u, let's just do a little bit of maybe like side working. Where can I put my side working? Down here. So u dot u. So using the formula that's on the formula sheet, this one here, that would say the magnitude of u times the magnitude of u times the cosine of theta. But that theta, remember, is the angle between the vector, the two vectors. But this is the vector in itself. So it's the angle between the vector u and itself, which has to be 0, right? And the magnitude of u we've already got. So we can fill out this equation as 4 times 4 times the cosine of 0. Cosine of 0, thinking about the cosine graph, that's like at the very start of the graph, that's up at 1. So this is 4 times 4 times 1, otherwise known as 16. So a bit of side work in there, again, using the formula from the formula sheet. Not easy though to piece this all together. So that there is just 16. So we get 16 plus u dot v equals 21. And if we think about where we are with the question, remember that we've already got this part here, and it's the u dot v part we're trying to get. So we've got u dot v here in our formula, in our equation, and we can just solve for it by subtracting the 16 to the other side. So it's going to be 21 minus 16, which is 5. So now we've got this part, and we've got these parts, which is everything we need to plug into our equation. So this here is going to be u dot v, which is 5, divided by 4 times 5. 4 times 5. And those 5s would just cancel, just leaving you with 1 over 4. So we're almost there. Now we just need to take the inverse. And if you take the inverse, that comes out to be 75.5 degrees. So cosine inverse of 1/4 equals 75.5 degrees. And that is the answer. Not an easy question, that one. It's a common question. Normally it's a little easier because you don't have to deal with using an alternative method to get this part. Normally the vectors are given in component form, so this one you could say is a bit more into the realm of problem solving. In part A of this question, we're asked to find the equation of the tangent line at P. So a tangent line, remember, is just a line, and if we're finding the equation of the line, a line, we're going to be using the y minus b equals mx minus a formula. And the criteria for using that formula is just that you've got a point on the line, which is AB, and you've got the gradient. So we've already got a point, 5, 13, which lies on our line, so that criteria has been met. So the challenge is to find the gradient. We're going to find the gradient by making the gradient of C to P. So C is the center of the circle, therefore C to P is the radius, and a radius line and a tangent line are always at a right angle. So if we can establish the gradient of the radius, we can use the rule for perpendicular right angle gradients to get the gradient of the tangent line. So let's start by doing that. So we're making the gradient of CP. So good to use a little subscript to identify your different gradients. So that's just going to be using these 2 points here. So we're going to get 13 minus 12 over 5 minus 8. Okay, so just working that forward, 13 minus 12 is 1. Slightly concerned I had to think about that. And then 5 minus 8 is negative 3. So if you just check the diagram, does that make sense? I'm just looking at the diagram. So yeah, that is a negative gradient. So the line is sloping down the way to the right. and it's quite shallow, so the 1/3 looks fine. So always check your diagrams to make sure you get the correct sort of orientation for your gradients. So we're looking for the line that's perpendicular to that, so M sub perp, or you could call it M sub tan for tangent. So using the fact that gradients, if they're perpendicular, they multiply together to make -1, or you can just call it the negative reciprocal. So the negative of a negative number is a positive number, the reciprocal is when you flip it. So in other words, the other gradient, the one we're interested in, has to be 3. And you could check that by multiplying these together, and they should come out to be -1, which they would do. Okay, so our tangent line has got a gradient of 3. So that tells us we've now got both of the bits we need. So we can plug into our formula. So it's going to be y minus b. So it's going to be y minus 13. Remember, it's only this point that's on our line. This is not on our line, that's in the circle. So it's going to be y minus 13 equals the gradient, which is 3x minus the a value, which is 5. Okay, and then just multiplying out the bracket. So y minus 13 equals 3x minus 15, and then we get y equals 3x minus 15 plus 13 is minus 2. And again, checking your diagram, always good for straight line questions in particular. You can see that the y-intercept there, which is point T, which is the next part of the question, could be at -2. So that kind of fits in with the geometry, just helping to validate that that could be a correct answer. So moving swiftly on to part B, part 1, it's asking us there to state the coordinates of T. So T is the y-intercept of the line that we just made, the y-intercept of 3x minus 2. So formally you would do this by saying, well, if it's on the y-axis, then the x value is 0, so you put a 0 in here. But we also just know that the end value is always the y-intercept. The only thing to be careful with is to state the full coordinate. So if you write down t equals -2, you will not get the mark. The full coordinate of t is 0 minus 2. Okay, so be really careful with that. And notice that it is just a state question, so there shouldn't be any working to do. It's just a case of writing that down. Okay, in the third part of the question, find the equation of a circle passing through C, P, and T. Okay, so if you're ever trying to find the equation of a circle, a little bit like if you're trying to find the equation of a line, use this formula. If you're trying to find the equation of a circle, we're going to be plugging into the basic circle equation, which is x minus a squared plus y minus b squared equals r squared. And in the same way that the criteria to use this formula is to have a point on the line in the gradient, the criteria to use this formula is to have AB, which is the center of the circle, and to have r, which is the radius. How are we going to get that? Well, we're going to get that by realizing that P to T is a diameter. So if we can figure out the distance between those 2 points, so it's going to be the distance between the points P and T, that would give us the diameter of our circle. We can then just half that to get the radius. And then we'll do that first, and then we'll worry about the center point after that. So these are the 2 points we're using. I'm just going to pull this one over. So P is the point at 513. We're trying to find the distance between those 2 points. So we can use the distance formula. So that's just equal to the square root of the difference between the x's squared. So that's going to be 5 minus 0 squared. And the difference between the y squared, which is 13 minus 2 squared, like that, and then just carefully working this forward. Remember, it's a calculator question, so you could just put it in the calculator. That's going to be 5 squared. This is going to be 15 squared. Okay, like that. And let me just check what that comes out to be, because I calculated it earlier. Oh yeah, 250. So that becomes the square root of 250. Okay, so we could simplify that at this point, or you could leave it like that. That's maybe kind of personal preference, but one thing to be really careful with, that remember is that is the diameter of our circle. So the radius is going to be half of that. Very tempting to say, well, half of 250 is 125, so the radius must be the square root of 125. Doesn't quite work like that because of the square root. So this actually being the diameter, this actually implies that the radius is just that number, root 250, halved divided by 2, like that, okay? So you can check that. If you can check that. If you make this a square root of 125, and if you take this number and evaluate it, they're not going to be the same thing. So that basically gives us our radius. Now we need to get our center point. Well, the center point is just the middle of these 2 points, isn't it? Like these are extreme ends of the diameter, so the middle must be the center. So the middle of these 2 points you could get by just adding them together and dividing by 2. So I'm just going to put this here for center. And maybe I'll call that C1 because there's another C in the question. So just identify the center of the circle we're currently working with. So yeah, the middle of these 2 points is going to be the middle of 0 and 5, which is 2.5 or 5 over 2. But you can always use the midpoint formula, which says add them together and divide by 2. 5 plus 0 is 5, divided by 2 is 5 over 2. Same with these guys, 13 plus minus 2, that's 13 minus 2, which is 11, and then divide that by 2. So the center comes out to be a slightly awkward set of coordinates for this one. So that means that we've now found our radius and we've found our center point. So we can go ahead and plug them into this formula. So basically I'm just plugging this into here. So we're going to get x minus the 5 over 2 value, which is the x coordinate of our center point squared, plus y minus the y coordinate of the center point, which is 11 over 2 all squared, equals the radius, which remember is this number here, root 250 over 2 squared, because remember the formula is r squared. Not a huge amount you can do really on the left hand side, but we would just keep that the same. On the right hand side we can tidy up, because the square root of 250 squared, square root and a squared, remember, just cancel, so that would just be 250, and then 2 squared is 4, so it ends up being 250 divided by 4. And you could maybe leave it like that, or you could chuck that in the calculator to get a decimal number. So just pulling that down to get the final answer. So I think if you put that in the calculator, it comes out to be 62.5. Okay, so that is the circle we're looking for, and that's the end of that question.